Hello chemists, this is Ms. Placino and you are watching Screencast 9.4 on calculating delta H. In today's lesson we're going to talk about how to calculate changes in enthalpy. That's what delta H is. It's also called the heat of the reaction, using heats of formation data. So in the previous lesson, 9.3, we were introduced to delta H through potential energy diagrams. So we can very readily calculate delta H by looking at a PE diagram. Sometimes potential energy diagrams aren't always going to be available, so we need to learn how to calculate delta H using what's called thermochemical data. Don't worry, it sounds a whole lot more complicated than it actually is. Today's lesson is pretty into calculations, so you're probably going to want a calculator, and make sure that you're actually trying to do the calculations along with me and not just watch me do them. I don't want to brag, but I'm pretty good at introductory level chemistry. Make sure you can do it for yourself. All right, let's get into the lesson. So we know that enthalpy is the quantity of energy transferred as heat during a chemical reaction. We talked about this in the last lesson. We can find the delta H of the reaction by taking the enthalpy, or again, we can just think of it kind of as energy of the products, and subtracting out the energy of the reactants. That's it. It's always where did the reaction end up as far as energy concerned, and subtract out the energy that the reactants initially had. We talked about exothermic and endothermic reactions yesterday. We'll start with exothermic. In an exothermic reaction, the delta H, or the change in enthalpy, is negative. Here's a PE diagram. If we think about the formula, delta H is equal to products minus reactants. Hopefully it's very clear why delta H is going to be negative. The products have less energy than the reactants. So here's some examples. We've got a very generic reaction, A plus B yields AB plus, now we've been a little bit more specific with the heat term, plus 100 kilojoules of energy. That means that 100 kilojoules of energy are being lost or emitted as the reaction progresses. And another way we can write this is A plus B yields AB, and then off to the side somewhere we can write delta H, or the change in enthalpy of this reaction, is 100 kilojoules. Negative. It's really important. The sign here is huge. Negative 100 kilojoules. If we contrast that to an endothermic reaction, similar PE diagram, except now the products have more energy than the reactants. Therefore, when we subtract enthalpy of the products minus enthalpy of the reactants, we end up with a positive number. That means the energy is being absorbed. So if I go in the opposite direction, instead of synthesizing AB from A and B, let's undergo a decomposition reaction. So AB plus 100 kilojoules of energy will give me A plus B. Another way to represent that is just showing the equation and then off to the side writing a delta H value. In this case, delta H would be equal to positive 100 kilojoules. It is not a coincidence that the forward reaction, the synthesis of AB, is exothermic, and the reverse reaction, the decomposition of AB, is endothermic. This is true for every reversible reaction. If the forward is exothermic, the reverse is endothermic. If the forward is endothermic, therefore the reverse must be exothermic. And we just flip the sign. So the number, the numerical value, doesn't change, but the sign does, because the sign is telling us whether heat is being released, exothermic, or heat is being absorbed, endothermic, by the reaction. So let's talk a little bit about what the New York State Regents exam is going to expect from you as far as enthalpy is concerned. In a typical fashion, New York State has set the bar low. They're really concerned with can you read, not can you do chemistry. So they've given you table I, and I have a fraction, or some portion of table I here. So this is our heats of reaction, delta H values at 101.3 kPas and 298 K. So 1 atmosphere pressure and about room temperature, 25 Celsius. Delta H is proportional to the coefficients in the balanced chemical equation. So let's just pick one of these. Let's see, I'm going to look at, let's do the synthesis of water, because that's a reaction that I'm guessing most of us are pretty familiar with. So we've got, and be careful, there are two syntheses of water. One gives you gaseous water, one gives you liquid water. I've arbitrarily picked the one that's a gas. So here we have 2H2 plus O2 yields 2H2O gas, and it's telling us that this is an exothermic reaction, and it's going to release 483.6 kilojoules of energy. Let's say I go through and instead of joining 2 moles of hydrogen and 1 mole of oxygen, I double that. I use 4 moles of hydrogen and 2 moles of oxygen to produce 4 moles of water. If I double my coefficients and delta H is proportional to the coefficients, what do I need to do to calculate delta H? If you're thinking, well, just multiply that by 2 because you multiplied all the coefficients by 2, you are absolutely right. Excellent. If you need to reverse the reaction, then you just simply flip the sign or negate or invert, however you'd like to think of it, but change to the opposite sign of delta H. So if we continue to use this synthesis of water reaction as an example, let's say I go in the opposite direction. Instead of making water, I'm going to take my water and I'm going to try to decompose it and turn it back into hydrogen and oxygen gas at a 2-to-1 mole ratio. So I've reversed the reaction. What should I probably do to the sign of delta H? Well, the number stays exactly the same, but the decomposition of 2 moles of water is going to require 483.6 kilojoules of energy. Therefore, I just need to change the sign to show that it is an endothermic reaction and have positive 483.6. That's it. If you can follow along with that, you are in pretty good shape. So let's try out some practice problems. All right, in your workbook you have a handful of practice problems, and most of this just comes down to using table I correctly and making sure that you know those 2 rules. That delta H is proportional to the coefficients, so whatever you need to do to the coefficients from a mathematical perspective, whether it's multiply or divide, also needs to happen to delta H. And if you reverse the direction of the reaction, if you take a synthesis and you turn it into a decomposition, the numerical value of the enthalpy term does not change, but the sign does. So let's walk through one of them together, and we'll let you try out the other ones on your own. So question number 1 is asking how many kilojoules would be released if 6 moles of NH3 were produced from its elements. Okay, so if you look at table I, you can find this reaction. N2 plus 3H2 yields 2NH3, and this has a delta H value of negative 91.8 kilojoules, so the negative is telling me it's exothermic, so I'm okay to put my products, I should say heat, as a product. So I know that when this reaction occurs, roughly 92 kilojoules of energy are released. And what we want to know is how much energy is going to be released if instead of producing 2 moles of NH3, we need to produce 6 moles of NH3. All right, we got my 2 moles of NH3 right there. If I want to go from 2 and I want to get to 6, as you might guess, we need to multiply by 3. That's an ugly looking parentheses. 3. There we go. And whatever I do to the equation, I'm also going to do to delta H. So I now have 3N2 plus 9H2 makes 6NH3. And if I take roughly 92 kilojoules and I multiply by 3, hopefully that's a really easy one for you to plug into your calculator, you end up with around 274-ish kilojoules. That's it. Try out question 2 on your own. Okay, for question number 2, I've already gone ahead and solved it. If you look on table I, you can find the reaction 2 carbon plus 3 hydrogen yields C2H6, and the delta H value for that of negative 84 kilojoules. What we're trying to figure out is how much energy would be needed to create 4 moles of carbon by decomposing. So I have 2 moles of carbon in my equation. In order to get to 4, I need to multiply by 2, and I need to flip it, which is not asking us about delta H, so that's not super important right now, but we'll just be thorough. And I come up with about 168 kilojoules of energy would be required. Question 3 is very similar to question 1 and 2. Question 4 is a little bit trickier. It asks you to incorporate some information about the mole. So try those out on your own and definitely check out the answer key. All right, let's get back to the notes. If you look at Table I, you'll notice that there are only about, 24 or so different reactions listed, and in reality, there are way more chemical reactions that can take place. So Table I has a very limited use in the real world. Enthalpy, delta H of reactions are calculated all the time, and we need to use thermochemical data in order to do that. So at this point in time, this lesson is going to become a little bit more, real world style calculation instead of just simply using Table I. So here's where you really need a calculator. There are values called molar enthalpy of formation, or heats of formation, and we use this notation. And this is the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard states at 25 degrees Celsius and 1 atm. At first pass, this might seem kind of confusing, so let's break it down. Heats of formation is basically the change in energy that occurs when you make a compound from its elements. Sometimes when you make a compound, it is formed exothermically, and joining the elements together is going to release energy. Other times when you form a compound, it occurs endothermically. So when you take the original elements and you combine them, energy is absorbed from the environment or from the surroundings. If you have an element in its standard state, so basically an element in the phase that it exists at 1 atmosphere of pressure, and I think they say either 0 or 25 degrees Celsius, it's escaping me right now, it has a heat of formation of 0. For example, O2 gas that has a 1 atmosphere of pressure and 25 degrees Celsius, it's going to have a H sub F of 0 because it exists as a gas. The more negative the delta H of formation, the heat of formation is, the more stable the compound is. By their very nature, compounds and elements want to be in the lowest possible energy state. So the more negative delta H sub F is, the more energy that was released to produce it. So you can think of it as the lower in energy that compound is. Stay with me. I know this can be confusing. When we go to calculate enthalpy in the real world, we cannot use Table I. Again, it's really limited. So we have the change in enthalpy of the reaction, or the delta H of the reaction, is equal to, you might know from math class what that symbol is. That's a summation sign. N is moles, so the total number of moles of the enthalpy of the products minus the total moles, the enthalpy of the reactants. So let's get that down. Delta H is the total change in enthalpy over the course of the reaction. It's still products minus reactants, except now we've got a little bit more detail. The moles of the products times the enthalpy of the products, subtracted, and then subtract the moles of the reactants times the enthalpy of the reactants. This can be kind of difficult to think about abstractly, and once we really start to put it into practice, it is a lot easier to contend with, I promise. You might be wondering, where on earth do these numbers come from? Well, N is simply the balanced chemical equation. You're going to use the coefficient, so the number that comes before each substance, whether it's a reactant or a product, in the equation. And the delta H of the H of the products and the reactants come from a data table. And this will either be provided to you in any question I ask you, or I'll just give you the whole table and you can look through it. So let's look at calculating the change in enthalpy for this reaction. We've got CH4, which is methane, reacting with oxygen to create carbon dioxide and water, a combustion reaction. First thing you want to do is go through and balance it. So hopefully by now balancing has become kind of second nature. We get these coefficients. I'm going to provide to you the heats of formation. And I'll show you what a table looks like in just a little while. But when methane, CH4, is formed from carbon and hydrogen, negative 74.8 kilojoules per mole is the result. So forming this releases energy. Because oxygen gas is in its standard state, it has a heat of formation of 0 kilojoules per mole. Carbon dioxide, negative 393.5 kilojoules per mole. And water is negative 285.8 kilojoules per mole. We're going to use this formula. Delta H of the reaction is equal to the summation of moles enthalpy of the products minus the summation of moles enthalpy of the reactants. Before we start putting numbers in there, let's talk about what this is going to look like. It's always products minus reactants. And if you look, you have carbon dioxide and water as your products in a 1:2 ratio. And here they show up here. I've got carbon dioxide times 1, so I didn't include that term, plus, because it's summation of moles, 2 moles of water. I can do the same thing for the reactant side. I have CH4, 1 mole of that, so just CH4, plus 2 moles of oxygen, 2 times O2. And it's products minus reactants, so I need to subtract. Let's start plugging in some information. So where we've got CO2, I'm going to sub in negative 393.5. Well, 2 is going to stay, that's not a variable. For water, I'm going to plug in negative 285.8 kilojoules per mole. And I'm going to subtract my H value, my heat of formation. For CH4, negative 74.8 kilojoules per mole. And I'm going to do the same thing for oxygen, 2 times 0. So that one's really, really simple. So it's going to look something like this. Those are the numbers we talked about. And I know that I have skipped out on units here. It's really in the interest of space. But if you look at it, you're taking kilojoules per mole as far as your H value is concerned. And you're multiplying, by mole. Or sometimes you're just multiplying, they'll just use this as a constant, and then the mole doesn't end up canceling out. At this point in time, if you can do the math, I'm really excited, and whether you want to call it kilojoules per mole or just kilojoules, we're going to take it. I simplified, you don't have to. And when it's all said and done, I calculate a delta H at negative 890.3 kilojoules. And since this is a negative delta H, that means we have an exothermic reaction. This seems like a lot of work, and I understand that, and it looks overwhelming, especially with those summation signs thrown in the formula. But if you can really follow this procedure, you can solve really any delta H problem that I throw at you. And there are a couple other things that we're going to solve for this unit that can be calculated the same way. Products minus reactants, where you take the coefficient, or the number of moles of each substance, you multiply it by, in this case, the heat of formation value, and you take products minus reactants. That's it. So in your 60-second summary box, I think it's really a good idea to create a step-by-step procedure for calculating the delta H of a chemical reaction. I know that, again, it doesn't seem too terrible maybe when we're going over it together in the notes, and then you go to look at it, outside of class or the next day or when you're studying for the test, and you're kind of confused about what you did. So take the time to come up with a brief procedure. There are more practice problems, of course, in the workbook. Try those out, and as always, compare your answers to the key that I've posted online. Stay with it. The math itself isn't too complicated. It's just multiplication, addition, and subtraction, but I understand conceptually this can be really challenging. So don't give up. Keep practicing with it. We're going to be spending more time in class just to help you get comfortable with the calculations. Thanks for tuning in, and I hope you found this helpful.